experiment head losses in pipe flow. So I have the hard copy, and you can open this soft copy in your system so that if you have any doubt or any queries, we can address directly. So anyway, so any doubt so far regarding the experiment? Who watched that video? If not, then we'll start with some simple discussion about the pipe flow. Anyone? Any question? I guess not. Then we'll start our discussion. Uh, so the question is, okay, the topic of this experiment is to find out the head losses in pipe flow, right? So when you talk about the losses happens due to multiple factors. Okay, we will come to that different factors which influences the losses in pipe flow. But before that, just tell me why the flow happens. Any idea, anyone? Why there is a flow?
Due to pressure difference applied.
Yes, who said that?
Says Vinayak.
Vinayak, yes, right. So if there is a pressure drop, I mean, mainly we are concerned about the pipe flow in this in this experiment. So if there is a pressure difference between two different points across the pipe, then we expect that, or naturally it happens that there is a flow inside the pipe, right? Now, when pipe flows, so what happens with the pressure drop? Anyone? So say for example, there is a pipe. So just imagine, I mean, I do not have the soft copy, so that's why I'm just verbally asking you this question. You just try to think. You have a straight channel or straight pipe with circular cross section, and the fluid flow happens between point A and B. A at the left side and B at the right side. So upstream and downstream. These are the two conventional terms people use in pipe flow. Now, how the pressure varies? Anyone, any idea?
So pressure drops from A to B.
Sorry, pressure drop.
From A to B.
Can you please just say it a little bit loud, because there is a function going on around my place, so it's getting a little bit difficult to listen. Can you please a little bit loud? It's Meghna, right?
Yeah. So like I was saying
Yeah,
that
Vishruta.
yes, we
Yes,
both are saying then
Let me increase the volume of my system, because let me see. But you can hear me loudly, right?
yes, sir.
Anyone?
Yes, sir.
Okay. But anyway, unfortunately, I cannot hear you clearly. So
Is it
yes.
fine?
So sorry.
Am I audible right now?
Yes. Yes. Now you're audible.
Yes, sir. Like I'm saying that if it's a laminar flow, then the pressure drop might be dependent on the Hagen-Poiseuille equation.
Yeah. Yeah. But how this pressure changes from one point to the another point towards the downstream?
Because of the velocity.
Sir, it
Yeah.
follows
Yeah.
Darcy's law.
Sorry.
Darcy's law is followed.
Darcy's law followed. That is true. So just try to think the physical phenomena. So you have given, like, say, for example, pressure P1 at the entrance. There is a certain length of the pipe L, and at P2 we are getting the exit of the fluid. So the pressure will decrease from inlet to outlet, right? And the Darcy's law, it's Vinayak who said that, or who?
Sir, Hemant.
Sorry?
Hemant.
Hemant, yes, Hemant. So if you remember the lecture note, it's probably lecture note 25 and 26 in the fluid mechanics course. It's Darcy-Weisbach law, right? And from that we derived this Darcy's coefficient. So yes, the Darcy's law is essentially explains the friction losses. or the major losses, right? So the pressure will see, these are the very the interesting questions, and if you think, you will also essentially get the answer. Just try to imagine. So the pressure decreases from inlet to the outlet, and if you imagine that you have a pipeline that is 5 kilometers long, and if the pressure drop or the inlet pressure is not sufficient, in the middle multiple sections you need to apply extra pressure again to continue the flow, right? And that happens because of certain resistance that is inherent in any kind of flows. Now, if you think about Newton's law of viscosity, we talked several times that the fluid layers moves on top of each other, right? Now, if there is a motion, there is a friction. Friction can be dry friction, it can be wet friction. Dry friction, you studied in high school, that if two solid surfaces moves over each other, there is a friction, right? The same thing happens when fluid flows. So it's within the fluid, different layers are moving, and they, due to the relative motion between these two layers, there is a friction, and from that you can also get the expression for viscosity, right? Now, along with that friction, once we think about the flow in a pipe, the fluid also interact with the solid boundary. There also you can expect some friction. So these two frictions, I mean, all those informations are there in the introduction and the theory part of the manual you have. So those two frictions comprises this major loss in pipe flow, right? Along with that, we can also expect different kind of losses if there are different connections, different fittings, change in direction of the flow. Then also we get different kinds of losses. Those are called minor losses. Now the major objective in this experiment is to find out those losses and the loss coefficients. And all those expressions are there. It's already clearly mentioned in terms of this Darcy's equation. So and also the general equation for this loss coefficient, and minor loss heads. So those things you need to calculate. In the manual also you will get the diagram of the pipe flow, different pipe connections. Essentially, we are going to measure the losses in two sets of pipes. One is stainless steel pipes. One set is stainless steel pipe. Another set is galvanized iron pipe. Okay, those galvanized iron pipes are also usually zinc coated, but those are some auxiliary information for you. And those coatings are there just to reduce this what's called this corrosion of the material. So if you are flowing some fluid in any pipe or any channel, over the period of time, you are expected to get the corrosion, right? So that can be avoided or that can be reduced. And these GI pipes are very cheap and fragile also. So these kind of pipes usually used in our experiment in our department. And also you can see in the diagram that there are different valves and also different elbow connections. So even if you particularly those who has houses in the rural areas, there you can see that from the water tank you are getting water at your sink, right? So if you follow the pipeline, you can see that different connections are already there. So those connections are also contributing the minor losses in pipe flow. Okay, a similar kind of design is also there in the manual. So you just need to get those kind of head losses you need to calculate, and for that you need different parameter values, and most important parameter values is basically the volumetric flow rate that you can get, that you will be supplied this volumetric flow rate. From volumetric flow rate you will get the value of the average velocity of fluid flowing through different pipes. Okay, and from that you need to calculate the friction factors or friction coefficients and different other values for K, that is this the loss coefficient. Those are given for different valves and different elbow connections. You just need to plug in all those values. Everything is clearly mentioned in the manual. You just need to plug in one by one all the parameter values. Hello, anyone? Any question? No? So you just need to calculate those values, and from that you will get the final expression for final result for friction factor and loss coefficient. Those things you need to calculate. And one thing also you need to do, by the way, probably not everyone studied those lecture notes carefully during the course of fluid mechanics, because I heard that few students are not aware of this Moody's diagram or Moody's chart. Okay, so this Moody's diagram or Moody's chart will be very relevant for this experiment. So Moody's chart is essentially the relation between friction factor or friction coefficient with Reynolds number. So if there is a flow, you can expect the Reynolds number, right? And also it's unfortunate that not everybody is having a good understanding about the Reynolds number. So that's the primary number in fluid mechanics, or you can say that's the first letter of alphabets of fluid mechanics. So it's A of all the fluid mechanics non-dimensional numbers. So Reynolds number is very important and very crucial. Just try to get the physical understanding of that number. Okay. And this in the Moody diagram, it's a relation between F versus RE, the Reynolds number. You also need to plot the F value which you are getting from those experiments into the Moody diagram. That diagram also you need to mention in your report. Okay, so these are the primary things you need to mention in your the lab report. And what else? Yes, nothing else. And also in the discussion part, there are 3 points. So you just need to answer that one by one. Yes, that's it. And that's one of the simplest experiments you are going to write the report. So anyone, any more question?
So for the observations, we had given 3 observation tables, sir. So do we all have to do the 3?
Sorry, Meghna, what did you ask? Can you please repeat that question?
Is
Hello?
Is it fine?
Yes.
Sir?
Is it?
Yes, sir. Am I audible?
Yeah, you're audible.
Yes, sir. I'm asking that for the observations that had been sent in the mail,
Yes.
they had given 3 observation tables, sir. So,
Yes, all those will be supplied to everybody or every group. Okay.
So you're not audible.
Am I not audible? Am I
Yes.
audible now?
Yes, sir. Yes, sir. Now you're audible.
Yes. So the main data will be supplied to all the groups, or essentially everybody will receive the data. And from that data, you need to so if you see the diagram, so there you will see the inverted this YouTube manometer is there. So the height difference between 2 columns will be supplied. The volumetric flow rate will be supplied. Okay. So from that, you need to extract other parameter values that need to be plugged in the expression of F and H, or essentially K, the loss coefficient. Okay, Meghna?
Yes, sir. So we have to do for all the observation tables given.
Yes. All
Okay.
the data will be given for all the observations for table 1 and table 2.
Okay. Sir.
Okay.
Yes, sir. I'm asking that they had given 3 sets of different data, sir. In the mail. 3 different sets of mail.
Yes.
We have provided 3 observation tables. So, sir, every group have to choose one data set for.
Okay. Okay.
Oh, okay, sir. Thank you, sir.
Okay.
So we can choose anything, sir.
Yes.
Sorry?
Yes, you can choose one data set.
So one of the 3 data sets. Okay.
Okay, sir. Thank you, sir.
Okay. See, it's very simple and very straightforward. You just it's like arithmetic summation. I mean, just sum of different terms. So not very complicated, this one at least. And also just it's a request to all of you. Whenever you are writing this report, just try to understand the physics of any phenomena. It's not only for this course, but for any course. Okay, what is the background story? I mean, why you are doing and what is the main objective? How you can obtain those results? That's very crucial. The analytical understanding for any physical, because that's the role of any engineer, to understand the physical problem, formulate the problem mathematically, and provide the solution. Okay, so if you do not understand the physical problem, it will be difficult to formulate that problem. Okay, so that's why it's a request to all of you. Just try to imagine. Spend 5 to 10 minutes just to imagine. So just simple like that. You have a straight pipe of 1 meter length, say for example. Now, if the fluid is flowing through the pipe, the losses we just discussed, those are the losses. Now you are connecting that pipe with another same pipe. Okay, so then you need to add some connection, and due to that connection you are expected to one minor loss due to one connection. Now if you change the direction with another pipe, then another addition will be there, right? So just try to physically understand that thing. And then though all those understanding, you need not write it in your report, and there is no scope to write those things, but at least to get a clear picture of those experiments, it will be very helpful for any lab experiments or any courses you are attending. Just try to do that. I mean, that would be really, really helpful. Even once you will graduate, you will join in any different companies. They are also, if you grow this habit, if you grow this understanding, I mean, it will help you in your professional life also. So just try to spend 5 to 10 minutes to have a thought experiment, I would say. Okay, it will be very exciting also sometime. You can also discuss with friends, and if you are getting any doubts, just write it to me. I can also help you. Okay, so it's very simple anyway. In summary, it's a very straightforward lab experiments, and you are already supplied these data sets. Take one of these 3 data sets and just calculate all those values. Okay. Any more question?
So can you repeat that Moody chart thing again?
Okay, the Moody chart essentially gives the information of friction factor as a function of Reynolds number. Okay, now in the x-axis, you need to plot. I mean, the Moody diagram. I have. If you just go through the lecture note for fluid mechanics, there also I have drawn that, and also in Google, or you just search it, you will get it. But the plot in the x-axis, there is Reynolds number. In the y-axis, there is it is friction factor F. Okay. Now there are, as you all know, that when we classify fluid flow in macro scale, there are different regimes. Even in micro scale also there, but the number little bit varies. So you get laminar zone, you get turbulent zone, you get transition zone. Okay, the Moody chart gives you the clear demarcation of different zones with respect to friction factor. So in the laminar zone, you will get a relation of 16 by RE for friction factor. In the turbulent zone, there is no unified equation. Okay, but there are some empirical equations, and also the Moody chart is there to help you to get some data, and that Moody diagram is developed partly theoretically, partly experimentally. From different experiments, they collected the data. From that data, they created that chart. Okay. Now, in the turbulent zone, there are different lines also, horizontal lines. You will see. I mean, if you still have the access for that lecture material, you can listen it again. That along with that F versus RE, the plot of Moody chart also changes with the change of friction coefficient. So any material, if you can imagine, they are not atomically smooth. There is always inherent roughness in any material, right? Even if it is stainless steel. In also in many pipes, these roughnesses are created intentionally. to have the intentional friction loss. Now, anyone can tell me why this intentional friction losses is required? Anyone? I mentioned that in the lecture. If you can remember why the friction losses is beneficial in some cases. Anyone? Just try to guess. Anyone? I mean, for the chemical engineers, I mean the design was given based on the perspective of chemical engineers. That's why I'm asking. So if there is a yes, anyone?
Is it to maintain a smooth flow, sir?
Not really, not a smooth flow, but certainly flow. You are partly correct. So the thing is, for colder region or in the area where the temperature goes below 0 degree, or even goes around -30 or -40, even in some cases it can go even less. So particularly in oil industry, this is very useful in very colder region, because if the temperature goes down, what happens? Even if it is like above the melting point of oil, crude oil, say for example, what happens if you reduce the temperature? Anyone? Just try to think. So if the temperature goes down, the viscosity will increase. If the viscosity will increase, you need to apply higher pressure to sustain the flow. So as Meghna said, yeah, it is correct to have the flow, but how this roughness will help? Because of this roughness, there will be viscous dissipation. Where there is a viscous dissipation, there will be heat generation. And if the temperature goes below the melting point of the fluid, everything will be frozen. Then you cannot maintain the flow. So certain amount of heat needs to be generated to keep the material in liquid form so that you can sustain the flow. Okay, and that's why in many cases this roughness is essential. The friction losses you will get at the wall, at the boundary. Okay, and there are lots of fundamental studies also there, which is also related to the application, that why this roughness and what should be the optimum length scale of the roughness. So anyway, coming back to the Moody diagram or Moody chart, so in the turbulent zone you can also get the different lines, and that defines the friction coefficient for different roughness inside the pipe. This epsilon by d ratio is there. Okay, just if you still have the access, just go through the lecture note or the lecture video. I have explained that. So this Moody chart will give you a very clear picture for any kind of flow. Okay. So by the way, who asked about this Moody chart?
Sir Hemant.
Hemant. Okay, just try to.
Sir, I know about all these like epsilon by d. I'm just wanting to want to ask like what exactly do we have to show using that?
Okay. So yes. Okay. So okay. What you need to show is you will get the value of F, right? From the volumetric flow rate, you can get the value of Reynolds number. So where in Moody chart your data is fitting, that part you need to show. Okay. Hemant,
Okay.
is it clear?
So for example, we have one kind of a pipe. So
Mhm.
when we will change the Reynolds number, then the friction factor will change.
Yes.
But I don't think so. For a particular pipe, we have different kinds of different Q values in the experiment. So we don't have multiple points. Then how will we
No,
plot a curve?
no. If you have multiple velocity, you will have multiple Reynolds number, right? For a
Yes.
same pipe. So the value of F will shift. It may not change. You may have the same value, or you may have the same different value, little bit different value. But if you plot that in that Moody diagram, not plot, if you just point out the value you are getting, that will be the different value, right?
Yes, sir.
Because in your expression for F, there is the volumetric flow component is there. For high Reynolds number, you are right. For high Reynolds number, the value of F will not change. But at low Reynolds number, it will change.
Yes,
The friction
it's a
factor
linear kind of
changes.
flow.
Sorry?
In Moody chart, in the laminar region, friction factor changes like linearly if we plot on
Yes,
log versus log curve.
Yes. Also in turbulent flow, it changes up to, I forgot the exact value of Reynolds number. And at very, I mean, if you go very high Reynolds number, then it will not change. But the point is just to show, because your Reynolds number is changing, right? So say for example, the value you are getting is 0.16 or something. Okay. Now at Reynolds number 10 to the power 5, you are getting the same value. Also at 10 to the power 6, you are getting the same value. But you can point out in your Moody diagram that this is the value you are getting for at certain Reynolds number, and the different Reynolds number, the other the other value you are getting. Just point it in the Moody chart. Okay. Hemant,
Okay.
is it okay?
Yes, sir. Yes, sir. Thank you.
Okay. And I don't know what will be the Reynolds number in your calculation for this experiments or the data set you have already received. Just check with the Reynolds number, and then just to see the whether it is laminar zone or turbulent zone. Okay. Any more questions from anyone?
Sir, I have a doubt.
Yes.
You
What-
mentioned in the Modi chart for laminar zone we will get 16 by RE. So we
Yes.
get 16 by RE if we use fanning friction factor and 64 by RE if we use Darcy's law.
Yes.
So I just wanted to know when do we use which friction factor? There's a difference of a factor of 4 for the
Yes.
different friction factors.
So okay. So if you go with fanning friction factor, so there are two different fractions, and this fanning friction factor are rarely used. Okay. So those expressions are developed based on different empirical equations. Okay. But mostly the fanning friction factor is not. I mean, as of now I cannot strictly recall which one what. But it's based on two different expressions. You get these two different values. Okay. In the Moody diagram, they have used 16 by RE, right? Puru?
Sir, I think in Moody diagram it is 64 by RE because we use Darcy-Weisbach's law.
Just
Sir, in transfer
me.
phenomena we studied it was 16 by RE,
Yes,
if I remember.
but in fluid mechanics we studied 64 by RE.
Okay. So 64 by RE in the laminar zone, right?
Yes, sir.
Yes. So yes. Now I can recall. So okay. So this friction factor you get in Moody diagram. Okay. So that's actually related to fanning friction factor with a factor of 4, and that's why you get 16 or 64. Yeah. In Moody diagram you get 64 by R or 64 by RE in the laminar flow resin, right? Puru?
Yes, sir.
Yes. So with the fanning friction factor, it will be different.
So when do we use fanning friction factor? I just have this doubt.
When do you?
Where is the fanning friction factor used?
No. It's rarely used now.
Okay.
Sir, it's more kind of used in heat transfer and mass transfer.
Yes. But in fluid mechanics, I'm asking. I'm telling.
Okay.
Okay. But I mean, at the beginning, that was widely used in engineering problems. This fanning friction factor. Okay.
Okay, sir.
I mean, those equations are, as I mentioned at the beginning, that partly theoretically and partly experimentally, they have summarized all those general equations for fluid flow. Because for laminar flow, it's very fine and you can model that. But in turbulent flow, it's very difficult to model that phenomena, the fluid flow phenomena. And also to generalize for all kinds of pipe flow, that is very difficult. Is clear, Puru?
Yes, sir.
Okay. Any more doubt or question?
Just so we have.
By the way, yes, Agna.
Yes, sir. Like I'm asking that we have to show that Moody chart thing in the report, sir.
Yes. You just scan it from any standard textbook, or you can get it from online also. Okay, and just mark it the value you are obtaining for this experiment.
Yes, sir. That,
So, sir,
Okay.
just we have to show that how close those values are from the actual Moody chart.
How?
Whatever we are calculating using experiment,
Yes.
we just have to check that how is it
Yes,
exactly
yes,
with the
yes,
Modi chart.
yes, 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 yes.
Okay.
Okay. I'm sorry that my system is not. I don't know what's the issue with this. I cannot clearly hear all of you. So anyway, at least I can hear you partly. So that's the only important part, and also have clear understanding about the Modi chart, because in major exam also some might be asked. So just have just physical understanding of those of those situations and different diagrams and charts. Okay. Uh, any more question? No. So then we can stop our discussion if you do not have any more doubt or question.
Sir,
Okay. Yes.
I have not any, but sir, there is an issue in my submission. So can I ask you?
Yes. Yes. Yes, Rovin. There is an issue of what?
Sir, in submission of report.
Which report?
Sir, I mistakenly submitted a report 5 in place of report 6. So how can I submit my report 6, and how all these things will go right
Oh,
in right?
okay. The report six you had to submit before 2 p.m. today, right?
No, no, I am saying I have
Sir,
submitted
I'll
report
explain the
5
matter problem.
last week.
I'll do that. Sumrat sir, actually the problem is that the submission time is actually 5 p.m. today. But what Robin is talking about is for the previous week, that when the submission for experiment 5 is there, so
Okay.
he mistakenly submitted in the experiment 6 section, and he's not submitted the experiment 6 so far because he wanted to show MK sir that he's already done the previous work. I mean, for the previous week in time. So
Okay.
what he just
Okay.
what he
I
just
get it.
wants is that would he be able to upload the experiment 6 right now along with experiment 5 in the current submission link?
I guess you can. Those who got some confusion about the submission, that is fine. I guess that won't be a very big problem. So you can mention the report name clearly and submit. Okay, or you can email to the course coordinator, that is Professor Mohan. Okay, along with the instructor who was responsible for that particular experiment that you wrongly submitted in different link. Okay. Rovin?
Right, so that was MK sir only. So I mean, he had both of the roles, the instructor as well as being the course coordinator.
Okay, you can clearly send email to him. If you are not able to submit separately, that is fine. I think he will consider.
Right.
I mean, it's a nominal mistake. I mean, there is nothing a serious issue on that. Okay, but please confirm with him. Okay.
Thank you.
Okay. Now I can hear you clearly. I mean, I just removed this headphone. Now I can clearly hear you. Any more question or any more doubt? Just advice to all of you, and probably I need to advise to all the students in all the batches, and I already started from this master students as well as dual degree students and PhD students. Always try to think analytically about the problem first before you start mathematically solve, because see, you all can solve all the problems pretty easily because you are trained in solving numerical and mathematical problems. But before doing that, you need to go through another step, that is to understand the physics or the physical phenomena behind any problem. And believe me, that will help you in your professional life also in future. So please try to spend some time on that. Okay. So if you do not have any more doubt, and also if you really start thinking, always try to think deep inside. Even you can go at the molecular level also. Like for this experiment, say for example, Newton's law of viscosity, the two different layers. So these two different layers you will get when you think about the continuum approach. Okay. Now if you think about this molecular level, what could be the impact on that understanding? The momentum transport will come, and from that momentum transport you can also lead to Navier-Stokes equations for pipe flow or any flow essentially. Just try to think. I mean, that will be really exciting for you. Just try. Okay.
Yes.
So
sir.
any more doubt from anyone, like the issue Ravin had? Anyone, any other issues regarding the report submission or anything? No? Then we'll stop our discussion now. Okay. And also for all the experiments, try to get the relevant information that will be necessary for you to have a good viva in the major exam, during the major exam, because many students are not did not perform well, at least in the group I organized. So please try to get the background. See that will be really helpful for you to score high also for all the subjects. So just try to get those background information also. Okay. So anyone, no more doubt?
No, sir.
Okay. Ashutosh, it's fine?
Yes, sir. Yeah, it's fine,
Okay.
sir.
Okay. Then I guess you all received the data. So just write the report before next Wednesday. Okay. So
Right.
good luck for your report writing. Bye everyone. Then I will meet all the students in my section during the major exam, I guess. So till then, all the best to all of you.
Sure, sir. So please stop the recording as well.
Oh, yeah, I did not stop it. Yeah, now I'm stopping it.
Sure, sir.